95% confidence interval for mu sub big Y equals open curly bracket to big Y bar plus or minus 1.96 standard error of big Y bar, close curly bracket, and 99% confidence interval for mu sub big Y equals open curly bracket big Y bar plus or minus 2.58 standard error of big Y bar, close curly bracket. The clever reasoning goes like this. Suppose the true value of mu sub big Y is 21.5. Although we do not know this, then big Y bar has a normal distribution centered on 21.5, and the t-statistic testing the null hypothesis big Y mu sub big Y equals 21.5 has a big N of 0 and 1 distribution. Thus, if N is large, the probability of rejecting the null hypothesis mu sub big Y equals 21.5 at the 5% level is 5%. But because you tested all possible values of the population mean in constructing your set, in particular, you tested the true value mu sub big Y equals 21.5 in 95% of all samples, you will correctly accept a 21.5. This means that in 95% of all samples, your list will contain the true value of mu sub big Y. Thus, the values on your list constitute a 95% confidence set for mu sub big Y. This method of constructing a confidence set is impractical, for it requires you to test all possible values of mu sub big Y as null hypotheses. Fortunately, there is a much easier approach. According to the formula for the t-statistic in equation 3.13, a trial value of mu sub big Y naught is rejected at the 5% level if it is more than 1.96 standard errors away from big Y bar. Thus, the set of values of mu sub big Y that are not rejected at the 5% level consists of those values within plus or minus 1.96 standard errors of big Y bar. Of big Y bar, that is a 95% confidence interval for mu sub big Y is big Y bar minus plus, restarting that line, that is a 95% confidence interval for mu sub big Y is big Y bar minus 1.96 standard error of big Y is less than or equal to mu sub big Y, which is less than or equal to big Y bar plus 1.96 standard error of big Y. Key concept 3.7 summarizes this approach.